so this mini lecture is going to look at how we go from components of a vector to the vector value. If I know that an object is traveling, for example, an acceleration a velocity, has a certain velocity to the right and a velocity up, what is its overall velocity? If I solve a problem where I find the horizontal velocity and the vertical velocity, what's its overall velocity? We can do this with any vector. Velocity will be our example since we're in the motion unit. So if I know an object's horizontal velocity, it has a component velocity in the horizontal direction of 2 meters per second. And I know it also has a velocity in the vertical direction of 3 meters per second. Make that arrow a little bit bigger. What is the true velocity, the overall velocity of that object? And what direction is it going? Because velocity cares about direction. So if you're asked what the velocity is, it's not just about the size. It's about the size and the direction. And so we do this, we represented this pictorially in a previous mini lecture, but how do we get that number specifically? And we have to remember our trigonometry, and specifically Pythagoreans Theorem. So Pythagoreans Theorem tells us that it defines all the sides of a triangle for us. If I move my vertical velocity over here, as we can do with a vector, line it up head to tail, then the vector that I'm really interested in, the resultant vector between these two, is my true velocity. That looks like a right triangle, and we can use Pythagorean Theorem to find it. So as a reminder of what that magnitude is, a reminder of what Pythagorean Theorem tells us, it says that c squared, where c squared represents the hypotenuse, is equal to a squared plus b squared, where a and b represent the two sides. So if I know that my two sides, a is 2 squared, plus my other side, 3 squared, and I take the square root, my hypotenuse becomes the square root of 2 squared plus c squared. 3 squared. So if we do that mathematically, we get 4. Oops, that's not 4. 4 plus 9, which is 13, the square root of 13, which is 3.6. So in this example, the magnitude of my velocity is 3.6. That's just the magnitude. It just gives me the size. I don't yet know the direction. Before I get to the direction, let's make this a more generic form in terms of our velocity vector, or our position, or displacement vector, or it might be our acceleration vector or force vector. Whatever the component is, we're typically not going to talk about it as A's and B's. This was V horizontal velocity, V vertical velocity, and C was our hypotenuse, or true velocity. So it might look more like this if we're going to represent the physical quantities, that our velocity, and specifically the magnitude of the velocity. This is only going to get me that size. It's not going to give me the direction. Those absolute value bars represent magnitude. The magnitude of our velocity, or any physical quantity that is of a vector nature, is equal to the square root of its components, the sum of its components squared. So in this case, our horizontal velocity squared plus our vertical velocity squared. So representing the physical quantities in the Pythagorean theorem will help us reinforce that it's the physical quantities we're determining. Okay, so that gives us magnitude, but how about direction? Well, we again remember our trigonometry. So the direction is defined as the angle that the vector is moving at. Typically, we're going to describe that angle with respect to the positive x-axis. All right, so if I'm going to get that angle and I have the opposite and the hypotenuse, that is related to the tangent. So think back to that SOHCAHTOA. We know that the tangent of an angle is equal to the opposite over the adjacent. And I think I said that wrong. I have the opposite and I have the opposite and I have the adjacent. I think I messed that up. So go back. Just to be clear, our tangent, the angle that we're interested in with respect to the positive x-axis as it's drawn here, our tangent is going to give us the opposite over the adjacent. So I can take the inverse tangent to get my angle. of the opposite over the adjacent. And in this case, and in cases with physical quantities, I'm going to actually write this over here, we have the inverse tangent of the y component of that physical quantity, in this case velocity, over the x component of that physical quantity, in this case velocity. And that's our representation of the angle. So in this example, we have the inverse tangent of 3 over 2. And that gives us an angle of 56.3 degrees. All right, so pretty straightforward. But let's look what happens if I give us a different angle. So in the mini lecture on going from an angle to components, we looked at a vector that went to the bottom, so down and to the left. So let's do that example here and with our components and see what happens. All right, so let's erase this. I'm going to leave these two generic equations up so we can reference them and you can get used to seeing them in a form that is consistent with the physical representation that we're interested in this example and can be easily substituted for a physical representation of any vector. So what if I throw my projectile with some velocity v, but I know that that projectile has a horizontal component that is to the left and equal to a negative 2 meters per second, and it has a vertical component that is down and is equal to negative 3 meters per second. All right, so the first step is to determine the magnitude. So we'll use this relationship to determine the magnitude. And we see that the magnitude is equal to the square root of the horizontal component squared plus the vertical component squared. So again, that is the square root of 2 squared plus 3 squared. And we determined that, of course, to be 3.6 meters per second. So, as we might expect, if a vector is moving to the right and down, or the right and up, at the same component velocity as it is moving to the down and to the left, that its overall magnitude should be the same. And we find that it's the same. But what about the angle? So in order for us to determine the angle, we take the inverse tangent of the vertical component, negative 3, over the horizontal component, negative 2. And that gives us an angle of 56.3 degrees, which was the same angle that we got in this example. And I had told you that that angle it comes out with is going to give us the angle that's sort of relative to that positive x-axis. But there's a problem. These angles aren't the same. One's going down and to the left and the other is going up and to the right. What is our true angle in this case? Well, that requires us to remember what tangent gives us. In tangent, the inverse tangent, will only give us angles in 2 of the 4 quadrants. Quadrant 1 and quadrant 4. So when it gives me an angle in quadrant 1, that tells me it's going to be positive. And if I divide two negative numbers, I get positive. This mathematically looks no different than our previous example when these two were positive. So if I know both components are positive, then the angle that is produced out of the equation is in quadrant 1. But if I know both terms are negative, the angle that is produced is actually in quadrant 3. And it's along 180 degrees from the angle that I'm given. And so to get the true angle, what do I have to do? Well, this was 56.3. This is 180. So I add 180 plus 56.3, and my true angle for this example is 236.3 degrees. And that is with respect to the positive x-axis. Now there's of course multiple ways to describe this angle. We could say that it's 56.3 with respect to the negative x-axis. We could say it's 56.3 degrees south of the negative x-axis, or below the negative x-axis, because this angle here is 56.3 degrees. And that's fine, as long as you're clear. If you just give an angle, it is, by convention, always with respect to the positive x-axis. So know where your components lie. Just like in the last example, if you didn't use it with respect to the positive x-axis, you had to put those negatives in the mini lecture where we looked at the components from a vector. In this case, the magnitude will be appropriate, but you need to pay attention to what that angle is. All right. I'd encourage you to do a couple in the other quadrants, keeping in mind that if you have a vector in quadrant 4, your tangent is going to come out as a negative value. Remember that a negative angle is still with respect to the positive x-axis. It's just in the opposite direction of a positive angle. So if this is my angle and its magnitude is 25 degrees, because I'm going from the positive x-axis in the clockwise direction, this angle is negative 25 degrees. So if I get a tangent that's negative, that means I'm going in the opposite direction. I will only get values in the 4th quadrant, and so if I'm in the 2nd quadrant, I need to add that 180 degrees. All right, practice those other 2 quadrants. Good job.